Here we go. This is Chris Weedbrook from Xanadu.AI. Chris, thank you so much for doing this.
No problem. Thanks for having me. I appreciate it.
And we'll find out in the chat in moments now whether I've got the audio right or not. That's usually the first little part of these things is me figuring out the audio. But so yeah, I was so surprised to hear what was happening like around the corner from me, and you were very kind. I had a wonderful time with. Was it Raf? Was it Raf who took? Oh my God, Raf took me around the offices, showed me what was going on. But maybe you could explain to people what it is that you are, the amazing things that you were up to.
Yeah, thank you. So quite simply, we're building quantum computers in downtown Toronto.
I love that that's quite simple.
It's quite simple to say.
Yeah.
Actually, doing it is obviously another thing. But building these things in quantum computing, these quantum computers here in Toronto, and what is kind of unique, which you would have seen too, is that we're doing it on in a tower here in downtown Toronto.
Yeah.
So we have two full floors, the 24th floor, and where they're being built is on the 29th floor. So it's kind of wild. We have both full floors, so you can get 360 views of Toronto, which is pretty nice. But you're doing this world class craziness that's going to really change the world. In a tower that's above a supermarket, above Farm Boy.
Yeah, you've got like a dollar store in the basement. Yeah.
Exactly. Actually, so I arrived here in 2010 from Australia via Boston,
Oh yeah.
and when I first to work at University of Toronto, and I would walk past this building, for 4 years, and if someone told me, that a few years after that there would be a company that I'd be a part of building quantum computers, I wouldn't believe them because it just seems so surreal. So, but fast forward, we were founded in 2016. Fast forward, 8 or more years, we now have 220 people here. We have quantum computers. You saw some of them.
Oh yeah.
When we came, so they exist now. We're building. They need to get bigger, and that's what our next few years is all about.
How far along were they when you got into this, or are you literally at the beginning of this, the genesis of this stuff?
Yeah, well, there's a couple of things. So myself, along with a lot of people at Xanadu, particularly the early hires, we all came from academia. So we were contributing through in this field, specifically the field of photonic quantum computing.
So using light.
Using light,
Right.
that's
Yeah.
right. So an easy way to think about it is using lasers.
Right. Yeah. Lasers sound cool too. Yeah.
They
Yeah.
sound cool, yeah.
Yeah.
Particularly, we have a bunch of sharks here with lasers on their heads as well.
Isn't that's everyone's goal, isn't it, to get to the point with the moat and the lasers, and the
Yeah,
sharks?
that's it. I've lost any motivation to continue now that I will have that.
It's
So
just you're like cats, just playing with the lasers the whole time. It's
exactly. So that's kind of one of the building blocks of what we do here. And so I was part of the field of academia through my PhD and postdoc times, and so that was going on independent of the company. But then I started Xanadu in 2016 with the idea of how do we commercialize this research that a lot of us were a part of, and go beyond the research environment at universities, which is a lot of fun. But
yeah.
now you have the ability to have rather than a small team, you have hundreds of people working together
Yeah.
and on a very specific mission. So it's quite amazing how far we've all come.
There's a wonderful interview I saw yesterday that you did where you said quantum computing is really hard, but so's managing people. That you equated these two. That there's a
Yeah,
the
I
scaling up is difficult for both of them.
It is actually, and there's an old thing. No matter how deep tech or hard your technology is, the most challenging thing is still humans. The interaction of humans is a complex system,
Mm.
and so it doesn't mean that it's a bad thing. It just means that you have, you know, when you have more than one person, let's say you're in a marriage or in a partnership, that can be challenging.
Mm.
So that's just two people.
Yeah, multiply that by 200 now or whatever it is you've got. Yeah.
Exactly. We all have our own set of kind of rule books in our head. We all have things we want to work on. So I think it's challenging, but it's been a bit silly there as well, saying it's the hardest thing. It is hard, but it's not hard on a day-to-day basis.
Right.
Things
Right.
come up, we
Yeah.
solve them. But on the other hand, a quantum computer, you're challenging the very kind of microscopic laws of nature on
Yeah.
a daily basis. And you need to kind of get them under control. You need to leverage them to make sure this computer does what you want it to do. So it goes without saying how challenging that would be.
Yeah. It's a wonderful place to visit. I've got to say, there's such a wonderful there's a very it feels very dynamic. There's a lot of people all working on things. They all seem very excited about it. As I say, Raf, who took me around, is just, oh my God, what a gold mine of information. So how did you get into this? Like, how did you? Because I mean, you're literally in a field that just wouldn't have existed, really for people as an option 20 years ago.
Yeah, it's true. A lot of us that when we graduated, it's changed. I graduated from my PhD in '09, and there was really no companies that you could join. And so try to do a postdoc, or for those that still want to do physics, unfortunately they have to go to banking or consulting.
Right, right.
Nothing wrong with those fields, but if you want to continue doing what you're doing in your PhD or postdoc, there's no avenues. So for me, for me personally, my most proudest thing so far is the fact we've been able to employ over 200 people.
Yeah.
Having a job and a meaning and a purpose to go to every day cannot be undervalued, when it gets taken away from you. So,
right.
But my journey really started. I was when I was a teenager,
Yeah.
early teens. I would read books on Rockefeller, Henry Ford.
Oh, really? Oh, so you came at it from the business side.
Oh, for sure.
Really?
And
Okay.
still do to this day,
Yeah.
reading as much as I can. I just finished reading a book on Massa, two
Ha.
books on him, the SoftBank guy, reading another one about Andrew Carnegie now.
So you like reading the manuals?
Exactly. It's so funny. I'd rather read these books and kind of absorb stuff than read, say, a manual on entrepreneurship.
Right,
I think
right.
most people are kind of, like that as well. So I had that as a foundation. And then, I tried a few businesses after high school. They didn't work out. They were really nothing, but I was trying different things. Then I went back to university at 23 because I was okay at math, and I decided to do math. And then physics came up, and then I did a master's and then PhD in physics. But at each point was thinking, man, I wonder if sometime I'd be part of an industry that can commercialize this research.
Yeah.
So that's the entrepreneurial thing. So really the love of deep tech in terms of quantum computing and love of business in terms of entrepreneurship, those two things converged.
Well, and you really need that for something like this too, don't you? Because in that it's an industry that just didn't exist before. I was very surprised to hear your focus was on batteries. That's the research into batteries is what you're thinking these. Well, actually, let's step back for a second. This must be the most annoying part about doing what you do is having to explain quantum computing every single time you talk to someone. But in a nutshell, could you let us know what we need to know to talk further about this?
Yeah, it's kind of a magical thing when you think about it, but I try to simplify it so much and say, well, it's still a computer. We're very familiar with computers. But if you can make a computer out of quantum stuff, particles or photons, then you're going to see a new type of computer that can do things much, much faster. So I always give the example that the Xanadu team showed with one of our quantum computers called Borealis. With that computer, we chose a very specific math problem. So not a business problem yet, but something that we knew would be computationally difficult. Now, if we had run it on the world's fastest supercomputer at that time, which happened to be in Japan, and used all their 7.3 million GPUs, run it 24 hours a day, 7 days a week, it would have taken 7 million years to get the solution to this problem. So now we're talking, crazy numbers. But our computer, Borealis, that I mentioned, our photonic quantum computer, actually solved it in 2 minutes.
It's extraordinary.
So it's hard to really fathom. And so you go from 7 million years down to 2 minutes. So that's really the other example I give and what the expectation is. Things that would traditionally take millions of years can now take a couple of minutes. And more importantly, that was an important demonstration and stepping stone to what we're after now is how do you get those speed ups in important areas like drug discovery, material design, such as batteries that you mentioned, AI, logistics, and finance. And how do you do the same thing? Now, the counterintuitive thing there is that, well, in all these industries I mentioned, we don't wait 7 million years for drugs. We still have drugs. But so that alludes to there's two types of problems. One is problems that will take 7 million years, but other problems that would take a couple of years. And so we have drugs. And so it means that we're doing something. And that often starts with computational simulations. They give you candidates that you should try and then synthesize and then go through drug discovery trials. But,
so before you get to the physical, you're simulating them,
exactly.
and quantum computing is better at that, more efficient than that. I see. Okay.
That's
Yeah.
right. So
Right.
that's where you'll hopefully see, well, maybe not, you know, well, with drug discovery, it often takes 10 years, 1 to 2 billions of dollars on average, and then 90% of the candidates fail.
Right.
Now,
Yeah.
you could probably get to 100% succeed if you ran those computer simulations for hundreds of years.
Right.
But obviously, we don't want to do that because we would never have any drugs.
Hmm.
So you need to compromise. You need to say, well, I'm going to accept 90% failure because we need something to work, but you
Hmm.
still need that 10%. But wouldn't it be marvelous if we had a different computer just in the starting point that could actually flip that and give you 90% success rate?
Hmm.
And again, it's because you're working with these systems that are very complex that a quantum computer, we and others believe, are very good at solving. So that's kind of how they all tie together.
I love the image I always get with these things, and it's the only way I can sort of grasp it for myself is that the computers that we're all used to on our desk are solving a maze by trying each different thing, and it takes a long time to try all those different alternatives. Whereas the quantum gets to sort of almost try them all at the same time. So there's this wonderful sort of it's a very effective maze solver. Isn't it? Which is have I got that right? Basically, is that?
Yeah, that's right. That's depends who you speak to. There's some hardcore physicists that don't like
Yeah, I'm sure. I'm
that
sure.
explanation, but for the most part, that's a good way to look at it. And really, interference is playing a role. So
Mm,
in this maze example, you have things interfering destructively or constructively, like two waves in a pond.
mm,
And the goal is to set up algorithms in this maze example where you can actually work it so you're boosting the probability of the amplitudes interfering constructively and heading towards the right answer. So it is a remarkable thing, and like you said, it leads to, for certain problems, these incredible speed ups.
And are we still at a pure mathematics with this stuff, or is it, or are you sitting there going like, what if? I mean, is there like, I mean, how much of it is a sort of a 20,000 foot approach to it, and how much of it is actually in the numbers?
Well, here at Xanadu, it's the whole spectrum of things. So
Oh, right, because you're doing hardware to software, aren't you? You do the whole thing. Yeah,
we're full stack. So we
yeah,
do hardware. We make these photonic quantum
yeah.
computers, and we also build the software on top, which is our software is called Penny Lane.
Yes.
And then on top of that, there's also the algorithm team working at, well, what algorithms should we run on this computer once it gets large enough? So it really depends on where you are. If you look at the hardware, there's a team, for instance, that's building these things,
Yeah.
and also a team in hardware called the architecture team that's really pen and paper and simulations working out the mathematics of how
Mm,
to optimize these systems as well. From the algorithm side of things, it's really, what sort of algorithms do we have? How do we apply them to certain problems? Like you mentioned, we're working exclusively on batteries, and
mm,
bigger picture, it's really material design or quantum chemistry.
right.
So yeah, it's what's fascinating here. You have so many different people, over the 220 people that are working at very different levels of the computer in terms of building it. So it's quite incredible.
You've got this wonderful approach too, which I love. This whole modular approach to it, where you get your stable computer, and then you could just keep adding chunks to it until you've got what we need. They're saying, what do you need? Is it 1 million qubits you need before we can start doing sort of truly
That's right.
useful
Yeah,
stuff? Why a
yeah.
million? Why is it that's just a numbers game basically?
It could be, 999,000
Right,
qubits.
right.
So it
There's a
could
little
be
leeway, little leeway. Yeah.
Yeah, on average, it's that. And it comes to the fact that, well, the starting point is you want to do an algorithm. You want to do something that can take thousands of years, take it from thousands of years down a few minutes. And so you choose an algorithm. Pen and paper, you assume everything is perfect and it
Right.
runs the algorithm and it'll take a certain amount of time. But nothing in life is perfect.
Yeah.
And so you need to add, let's say you have 1,000 qubits that is needed to solve a problem. Well, in reality, you'll need 1,000 times 1,000. So you've got redundancy, and that's where the million comes from.
Mm,
Uh, Basically, you need error correction and fault tolerance. The computer's not always going to give you the right answer unless you really work on suppressing the errors. And the
right.
way you do that is by having redundancy, very much like in communication channels. Instead of saying A, I may say A for apple.
Right.
Instead of saying A, you've got the word A, the letter A. Now you've got the word apple, where it's
Right.
like, well, it's not going to be capple, it's not going to be baffle. Like that
Right.
doesn't make sense. So more than likely, you'll understand that it's A for because of the word apple. So you're adding redundancy, and this is where the million comes from. The million is what we call physical qubits.
Mm,
That's a redundancy, and out of that, you should be able to get around 1,000 good qubits or logical
Really?
qubits.
Wow.
Yeah, so you need about a million because ultimately you've got some redundancy, and that's also related to how many good qubits you need for the algorithm.
What stage are we at now compared to like the whole PC revolution? Are we still at the Apple kit yet? Can I build one of these?
You kind of can't build it, but you can use them. So
Right.
us and others in the industry have, so people can use it online. So
I
maybe
ran
what's
your Hello World program. I did your
oh, nice,
tutorial.
nice,
Yeah, it's great. It's great.
nice,
And
awesome.
that was using Penny Lane, right? That was access to Penny
It
Lane.
was
Yeah,
exactly,
that's
exactly.
fantastic. Use Python, my new favorite programming language.
Python,
Absolutely.
yep,
Oh, love
yeah.
it, love it. Yeah, yeah.
And it's kind of interesting. Let's go back to, I forget, Apple One came out maybe in '75 or
Hmm.
something around there. And imagine if you had the internet there. It's a really kind of interesting thought experiment. If we had the internet back then, per se, I wonder if the first use cases access will be, instead of buying them, you can just log in, pay a few
Yeah.
dollars, and use it online.
Hmm.
Of course, that didn't happen, but
But
you
that
know,
was how things were before that. I mean, it was all about getting terminal access to larger
that's
computers.
true. That's
Yeah.
true. But it wasn't. That's true. It wasn't in like a user friendly sort of
Oh no, no, no. You sort of had to bow to the acolytes of the computer. Yeah, yeah.
That's true. Yeah. So it wasn't really mass appeal then. But in terms of your question, where we are, it's really hard to sort of say. I've heard people say we're at the vacuum tube phase of the
Mm,
1940s.
mm,
But really, because we have computing already, it's not like starting from the beginning.
mm.
So we use a lot of classical compute already for our simulations. Our quantum computer has a lot of classical compute. So it's kind of, you can see some elements of the vacuum tube. You can see elements of data centers already. So
Mm.
it's a bit of everything, which is what you want. You don't want a new technology to be fully reminiscent of an old technology. You want to
Right.
say, well, looks a bit like that, it looks a bit like this, and through those similarities, you really create new technology.
Mm. And there's definitely a danger. I see it a lot of people comparing them to PCs all the time, and it really is a different way of computing, isn't it? I mean,
It really is, and PCs. I do believe you'll have a quantum computer in a laptop one day. The question is when. It won't be this
mm,
decade for sure.
mm,
But particularly with our approach, where in principle we can have nearly everything, and ultimately one day everything at room temperature. So no cryogenics, no laser cooling, no nothing. Where you can shrink it down using our approach, but not this decade. So it's more kind of like AWS or Azure, where you're
right.
booking time online to access these.
Which we're
NVIDIA
doing
should.
with traditional computers, anyways. I mean, the reality is, I mean, for some
Yeah,
of the Chat GPT, for some of the machine learning models, you've got online cloud computing. So yeah,
exactly right. Yeah, well,
yeah,
you wouldn't have the resources to do any training or anything like that. You're really
yeah.
accessing these large data centers.
It's amazing. And you guys, and the so the computer I would have access to do my program would have been one of your wonderful fridges that are running in the tower there.
Yeah, so it depends. What's great about Penny Lane is it doesn't care what hardware you use. So
Ah,
you can actually log in and create an account and run stuff, and it just uses your computer. So classical compute, just to
mm,
play around. And, a Hello World example doesn't need
yeah,
powerful quantum compute.
right, right.
But it allows you to now start playing around with the language and using
Mm.
Python, like you mentioned. Or you can actually use Penny Lane as the gateway to our hardware or anyone else's hardware as well. That's what's very unique about Penny Lane. So, yeah, depending on what your goal is, you can use a variety of things to leverage Penny Lane on.
That's so smart because that's very similar to the early PC days where we're trying to figure out what is the operating system that's going to run this because obviously that's going to be whoever that player is going to be in a great position. Um,
100%. Yeah.
wow,
And
it's exciting.
it is, and that's why we've made Penny Lane open access, open source, and available no matter what hardware you use, is
Hmm.
because people really love it. They can use our hardware, that's great, but they can use anyone else's, and it is kind of a race to a million qubits.
Hmm.
And so, if some people don't make it to a million qubits, aren't sort of the first ones through the gate before the gate closes, then we can potentially get more users using our hardware,
Hmm.
provided we're one of the first few to get through, obviously.
Right, but it also covers your bases too because if you've got a system that can run on anything, that is an aspect of your business that I'm sure will be valuable as well.
True.
I mean, that's
Exactly. Yeah.
that's great. So I guess the next question is what is the promise? There's so much promise to these things. I'm curious to know why, batteries, material science is where you went. I would have, because the stuff I always hear about to start off with is like, oh, we're gonna break this, the cryptographic systems, and the banking's gonna collapse, and isn't everyone's goal to crack crypto, or cryptography?
Well, it's a really, when you go to raise money, and we've raised quite a bit. When you go to venture capitalists, it doesn't look too good when you say, I'm going to break the law with you.
Okay, yes, this is
So,
why I'm not in business. But that's certainly one of the fears that this thing will.
it is,
Yeah.
particularly from, we've received so far about $40 million USD non-dilutive funding, both from the Canadian and US governments. And
Right, right.
that alludes to the fact that these, governments all around the world really need to keep an eye on this technology,
Yeah.
and will probably need to use it for this reason. Now, the good thing in terms of security, though, is quantum computers can hack current security, internet security.
Mm.
They're not big enough yet to do that. But in the meantime, you can actually, there's other codes or encryption techniques that a quantum computer cannot break.
So this is the
So
post
that's
quantum security stuff that, yeah,
exactly.
yeah. So we
Yeah. So
basically already solved that problem's sort of.
that problem's solved,
Mm.
but the implementation is not there yet. People need to implement it far widely. But what's interesting is that any government in the world can download any information now. So think medical records, patents, and other things that
Mm.
need to be secure potentially for decades.
Mm.
You can download that now. So if a large enough quantum computer is available in 10 years, you're going to have 10 years of information
Yeah.
that needed still to be secret. And so you can download anything now. It doesn't mean you can look at it or decrypt it. But so the longevity of certain information really matters. Let's
Mm.
say you and I were talking in secret today. Maybe it needs to be secret for 24 hours, but it doesn't have to be after that. And then it doesn't matter.
Right.
But there are longevity sort of use cases that I mentioned, patents, health records, they need to be secure for an average lifetime, so 80
Mm.
years.
Mm.
So that's why things need to be rolled out before a quantum computer gets big enough.
It's interesting. There's always this sort of shadow side to any wonderful new technology, because I mean the reality is we've been talking to Earth scientists, Earth observation scientists, and some more sort of environmentally friendly stuff, and they're saying, and space exploration, of course, and they're saying like we can go back to all this old data and use all these new technologies on it and make new discoveries. And you're saying yes, you could also go back and decrypt all of this stuff that's supposed to be secret. So yeah, we're amazing at figuring out horrible ways of using these technologies as well. So what do you think? Is Canada going to be a quantum power? That'd be rather nice, wouldn't it?
It has to be. And that's one of our mission is not that, but we need to do that. Our
Mm.
mission technically is to build quantum computers, make them useful and available to people everywhere.
Mm.
But you look at Australia. I'm originally from Australia. You see similarities there. Canada has not been great at commercializing
No,
these things.
no, yeah,
A lot of the talent maybe starts here, but then moves to the US.
yeah.
So we want to be one of the few examples where this does not happen, and we really want to be. There's a number of great quantum companies here in Canada.
Mm.
How do we become world leading
Mm.
and be really, Canadian at the same time? So it's doable. The Canadian government has invested a lot of money in terms of the talent, in terms of
Oh,
universities.
good, good. Okay, so they've been supportive.
Exactly, and that's through different institutes and universities. So we have the talent here. In fact, out of about 220 people, around about 50% are from overseas, but the other
Mm.
50% are homegrown talent. So not only are we giving jobs to people here from Canada, but we're also doing a brain gain rather
Right.
than the drain, which is really hampered historically. And a lot of founders want to first thing they want to do is go to the US. There's more money,
Yeah.
maybe more prestige, but hopefully we can set an example that doesn't have to be a first port of call.
Oh, that'd be wonderful. I mean, because it really is. I mean, look, we have the same issue with the film industry, where it's just you get to a certain level here, and then you go down the States because that's where all the money is.
Yeah.
Hey, if quantum, actually, now I say this, if quantum computing is so good at simulating, are we going to see quantum computing used to create some of the worlds we see in films and television stuff? Is that something or is it just too ridiculously expensive at this point?
Yeah, it's unclear. This is one of the things that's amazing about quantum computing. We have a lot of applications now, but I think most of the applications will come once we have 1 million qubits, or what
Right.
we
Okay.
call a quantum data center. People just playing around and discovering things. So it's so hard to predict the future in general,
Yeah.
but even more so with quantum computing. So who knows is the answer. It won't solve every problem faster. It's not going to load Facebook or Instagram or our
Yeah.
emails faster.
Yeah. Yeah.
It's unlikely. So, yeah, but the use cases are quite impactful if it does play out.
Absolutely. I mean, the battery one is fascinating because that's it. That is just such a. It's actually. Yeah, I'm very impressed with that as a choice because it's such a. It is such a problem right now. I mean, power, as always, is an issue, and we've got to become more efficient and more sort of, I guess, ecologically friendly with this stuff as well. We're almost at half an hour, so I should go and check and see if we've got any questions for you because I'm hogging all the time here. This is so I find this stuff absolutely fascinating, and I think it's one of my favorite things are a technology that you feel like you could be a part of. People could be a part of the beginning of this.
Yes,
They
yes.
can go in there, can start messing around with this code and trying out Penny Lane and saying, hey, why don't we use it? Oh, look, it works really well for this, or it's just so much fun. All right, I'm going to pull this up. Here's another question for you. I'm a big fan of Australia. I've been there a number of times now. Uh, what was it that drew you to Toronto?
That's simple. It's just work related. So I was finished my PhD in Australia, and it's typically you're encouraged to find a different group, preferably overseas, to work with.
Right,
So after that, I was a postdoc at MIT in Boston, and after that, I got a job in Toronto.
right.
And then that's where the story kind of started. Once I landed in Toronto, I thought I love Toronto. I'd love to stay here a long time.
Yeah.
And then just did two postdocs here at University of Toronto, and
Oh,
then
U of T, great. Yeah, yeah,
yeah,
yeah.
yeah, and then just decided to start Xanadu here.
That's fantastic. I'm just trying to get my into my email now because, of course, I've neglected to open that while we were talking. It's funny because Australia and Canada are very similar. I feel about
Yeah,
innovation. I think we're very. They've got some very smart, very well educated people, but they do tend to get drawn away from their own country, aren't they? I mean, it's a very similar issue.
yeah. I talk about on the one hand, I'm talking about how great Canada is, which is true,
Hmm.
but I did the same thing. I left my country of
Yeah,
origin.
there you go. There you go. Well, I mean, I like Australia and Canada. I feel have there's a nice bond there. I know whenever we went there, everyone was always the thing that I couldn't get over was that everyone was amazed that we could live here because how could you possibly live with bears? That was the thing that kept coming up for me. And I'm like, wait a second, you're surrounded by every poisonous creature on the planet, but you're worried about bears. All right, got some questions for you. This is from Aaron Fritz. Aaron Fritz asks, how do you keep the conductors from overheating?
Um,
The conductors. So what, the getting into the chip? What are the conductors?
I don't know what he means by the conductors there.
All right, so how do we keep the chips cold? I've seen these in action.
So the chips actually get quite hot when you control them, but yeah, I mean the chips just like any other chip doesn't heat up. So yeah, it's not an issue for us. In fact, what's really good about our chips compared to nearly everyone else is most of our chips actually run at room temperature. So no laser cooling, no cryogenics.
But how? I thought the whole point of the quantum thing was it has to be like cold and slow to work.
No, that's what's really great about our photonic based approach. So if you think of the ultimate goal of a million qubits or this quantum data center that I mentioned, then only 10% needs cryogenics. The rest is at room temperature. So we do have some cooling that you would have seen,
Right.
but it's far, far less in terms of the overall footprint. Now, we do need some cooling because you need to really escape from our world.
Hmm.
You really need to cool things down near to absolute zero so things are not really moving and there's less noise. But for the most part, a lot of our stuff, because we work in a regime of photonics that's different from everyone else pretty much, that we have the ability to actually be okay with room temperature fluctuations. They don't really cause us any problems.
So if you're not using photonics, you're using some kind of exotic materials of some sort. Is that the what are the different branches you can take with this?
Yeah, so we use photonics as the medium where we encode information on,
Hmm.
but we have a few different types of chips that or waveguides that the laser light gets coupled into. So we shine light essentially through waveguides. They're made of different materials, different types of silicon,
Hmm.
essentially. 3-5 materials for the detectors, and also the light will transverse through fiber as well.
Right.
So you have a whole bunch of chips, and then you also have a whole bunch of fiber optics that essentially make up our computer.
I couldn't get over watching someone actually putting together these strands of fiber. It's
Yeah.
just extraordinary. Okay, so how does AI go to help work out how to make it better or take over the world? All right, sorry. So this is a question from Glenn Corrigan. Says, how does AI go to help work out how to make it better or take over the world? I suppose. Yeah.
Take over the world. I can't comment.
Yeah, we can't speak to that. We can't speak to that. Yeah, yeah, yeah.
But we use a lot of, AI is, you hear it particularly in AI companies that are trying to raise money. They're all AI. AI is really, some people compare it to electricity, meaning that it's just there. We all use it. We don't even have to say we're using it, kind of thing. It's so prevalent. And so we're actually using traditional AI a lot in really end to end in our company. So one simple example would be we use it for chip design. So that's used there. We also use AI sort of techniques for things like the optimization side of our computer from a
Right, right.
theoretical point of view. It really is everywhere. We also have this cool thing the team did internally. We've got our own quantum chatbot on our Slack channel,
Oh yeah.
and that's trained on data that we care about. So, for instance, for our photonic architecture, we can ask it, things, what paper has this, or
Ah,
I can
smart.
ask it photonic quantum computing
Right.
questions, and it'll give us answers as well. It's still early days, but so really, it's just another tool. There's a lot special about it, but there's nothing special that we're kind of an AI first company. It's just everywhere anyway. So we look at it as another tool and see how that can help us build our quantum computer faster.
What about running AI on the quantum computer? Is there any advantage to that, or are we still trying to figure out whether that is the case?
Honestly, in the near term, we're still trying to figure out what that is. I do believe, along with others, it's going to be quite impressive. Once that's the field we call quantum machine learning or quantum AI. What's interesting at the heart of both of them, the mathematics is linear algebra, so that's a good start.
Right, right.
And in the long term, once you have a very powerful quantum computer, there's certain things that it can do that's quite remarkable for AI. In the near term, we're still trying to figure it out. The hope is, though, that we're hearing about the models are getting very, very complex just in general to train classically. Maybe once a quantum mechanical model that's still tough to train, but easy for a quantum computer could be a way to go. Another answer is we're still looking into is perhaps synthetic data. So I mentioned this quantum synthetic data. So I mentioned this demonstration that we did where it's generating information data that would have taken 7 million years to generate. Maybe there's certain synthetic data that would have taken 7 million years, but we can use it now. Now
Of course.
the trick is generating data that has value. We can generate data, but how do you generate data that has relevance to traditional machine learning problems? So a few things we're looking at now, but I'm sure something will materialize that will be very important in the near term.
And is this something? Are you really? Is this just like? Are you just grabbing the threads from all over the place, or are you having to ignore some and say like we're not focused on that. We're just going to focus on like material sciences or whatever?
Yeah, we're hardcore focused, and the reason is that let's take the battery as an example. It does have, it is transferable or applicable to things like quantum chemistry in general and other types of material design. So we do have that transferability. Having said that, if we focus on batteries, we're not battery experts. The team's getting there,
Right.
but it now means we have to partner with those people who are. And so we partner with a lot of the car companies, Volkswagen, BMW, Toyota, and so forth. They provide the battery expertise. We then have to hire people in batteries. And so you can already see that if we stretch ourselves too thin, like go to any of the other industries like
Yeah.
um, pharmaceuticals, drug discovery. So we'd have to do this all again, and we're
Right.
spreading us far too thin. So we also want to patent things that we do. So specialize in batteries is the first step, knowing it has applications outside of that in more general material design.
No, that's great. That's great. And I guess when you've got a new field that could be capable of doing anything, it's probably good to focus.
I think so, yeah.
How we do over time? I just want to make sure. I'm very conscious of the fact we've got you for an hour. Okay, so other questions. You have a unique background merging business acumen and physics degree. What top 5 books would you recommend reading for someone who wants to follow your steps? Ooh. Well,
Well, I wouldn't.
the Rockefeller one, I guess, is one of them. So yeah.
Yeah, there's the Rockefeller one that's called called Titan.
Mm.
That's great. I love the book on Steve Jobs and Elon Musk
Oh
by
yeah.
Walter Isaacson.
What
Those two are
the
great.
two together in one book?
No, just separate
Oh,
books,
I
but
see. I
I've
see.
read them. Yeah, I read them both a number of times now, and always come back to them. So, really, my recommendation is just find any biography that looks interesting to you.
Mm,
So
mm,
always start with from the point of view is what gets you excited, what do you
mm.
enjoy. So another one I've read many times, which I absolutely love, is Snowball, the book on Warren Buffett.
Oh
That's
yeah.
great. And a lot of these ones have that I mentioned, just thinking none of them have anything to do with quantum physics. Um,
You got any
you know,
quantum physics suggestions out there? Yeah.
well, I like the famous one on quantum information and quantum computing by Michael Nielsen and Ike Schwang.
Okay.
That's good. That's very technical, but
Mm,
that's a really fun one to
mm.
read. And also, I'm also been reading the last couple of months books on the first 25 years of quantum physics, and that's just fascinating.
Is that
It's
Feynman and
Yeah, not Feynman because he typically came after the
mm.
first 25 years. So the first 25 years starts at roughly 1900 to 1925.
Oh
So
wow. Oh, I didn't realize it was that far back. Wow. Okay.
yeah, yeah. Actually, 1925 is the year of quantum, 100 years. This year.
Oh wow.
But that would be the characters of Bohr, Einstein,
Mm.
Dirac, Heisenberg,
Oh
Schrodinger,
yeah, yeah.
all those guys. And it's just fascinating reading about how they came up with this stuff. A lot of it is just intuition, a lot
Yeah.
of it is mathematics, but a lot of it is crazy ideas, some that worked out, some that didn't.
Mm.
So that is very fascinating. And again, it comes back to, does this get you excited?
Yeah.
And if it does, read more. If it doesn't, choose a different topic. Find
Yeah.
that excitement, because it's a shame. It's a wasted life if you get up each day working on things you just don't find interesting.
Yeah.
I think that's really important.
Hey, that's why I do this. I get to every week. I get to talk to someone doing fascinating things, and I get to learn something in the process. So
Yeah, that's
it.
awesome.
And if people watch, fantastic. This you've just mentioned something which I have to bring up, which I know is so cheesy, but I was so delighted to hear this. The name Xanadu and its connection to those first 25 years
Oh,
of
yes.
quantum. Yeah. Do you want to let people in on that?
Sure. So I wanted to first call the company the Beatles.
Right.
That
Any
didn't
copyright
seem to work.
issues? Any? Yeah. No.
There could be problems there.
Yeah. Yeah.
And then I thought, well, how about McCartney? No. How
Yeah.
about Lennon?
Right.
No. And then I thought,
Wait, wait, no Ringo?
no, I didn't make the cut, unfortunately.
Because I think Ringo sounds kind of quantum somehow.
Yeah, yeah. Then I remembered one of my favorite bands was Electric Light
Oh
Orchestra,
yeah,
ELO,
yeah, yeah,
and that has light in it. So that's like,
yeah,
well, that's kind of cool. And then I thought, well, who was the lead singer? Jeff Lynne, and I
yeah.
saw him play with ELO. ELO's Jeff Lynne a couple of months ago in Toronto. It's fantastic.
Oh,
It's like, oh my God.
really? Wow, I didn't even know they were still playing. Jesus.
Yeah, it's their farewell tour, and Jeff Lynne. Anyways, I'm getting there. Jeff Lynne wrote the song Xanadu. And I thought, well, Xanadu sounds kind of cool. And I always loved as a kid the LP, the album from
Yeah.
the movie. Not the movie so much, but the
Yeah, the
record.
movie was a bit of a disappointment, wasn't it?
It
Yeah.
was.
Yeah.
The album is so good. Side one was Olivia Newton-John. Side two was ELO.
Yeah.
And so that's where the name came from, the song from the movie. But to your point, Olivia Newton-John, not many people know, her grandfather was Max Born, which was also, I should have mentioned, one of the leading physicists of the last century.
Yeah.
And she's Australian, and so that's kind of the journey.
It all feels very entangled, doesn't it? It feels very
It does. It
wonderfully
does.
quantum. Um,
Exactly.
okay, there's another question here. Between reading business books and biographies, do you read any or watch any sci-fi? Any pet peeves in how they portray quantum physics? Oh my God, don't even start me on that one. Or science in general. You any sci-fi at all, or you probably don't have time to read it, do you, or watch it?
I love movies,
Mm.
so therefore I love science fiction. So
Mm.
I'm not a Trekkie, but I love all the Star Trek movies. So
Right, right.
yeah, I watch all genres. I don't mind too much. It depends again how hardcore you are, but I don't mind that. Ant-Man had a lot of quantum in it.
It did have some questionable quantum, I'd have to say. Yes.
Yeah, and if you treat it as just a movie, it's fine, and it also gets people talking about quantum computing and maybe
Yeah.
seeing what is this stuff. So I think overall it's a positive thing. So I have no real qualms about that sort of stuff.
It's interesting though because there's some. I find that people come into these things. Often science fiction is seen as sort of the first stage of engineering. It's like the dreaming phase. Quantum seems like is a hard one because it's used as it's a very sort of easy solution to writing problems in a lot of these films. Um,
That's
uh,
true. That's true.
so any particular favorite ones that stood out for you? You sort of went, oh, I like that.
Mm, I can't think. Oh well, I love yeah. So I love anything by Christopher Nolan.
Oh, really?
Anything, and I always love how he's got like, he's got like I want to write there's always these genres and like a burglary sort of
Yeah,
thief genre,
yeah.
and then he combines that.
With Inception. Not
Yeah,
well. Yeah, there's Inception. Also, what was the other one?
Interstellar is
Oh, we just watched Interstellar again. Yeah,
yeah. I actually saw that. I went to Scotiabank and watched the 10-year anniversary on IMAX, and
yeah,
that was so good. So I love how he kind of brings, my favorite one of his is Tenet, and he talks a lot about a bit about Oppenheimer,
yeah.
and then the next one after that is Oppenheimer. So
Hmm.
his new one, I can't wait. That's going to be seems like a departure.
What is he
Matt
doing
Damon,
next? What's he doing next? Just
Homer's Odyssey.
oh, that's
Is,
right. Oh, yeah,
so
right.
that'll be fascinating to see.
Yeah, I wish they had that when I had to do that in school because I'd much rather watch the movie. It's a bit of a drag to read. Interesting. Yeah, that's interesting because I've always feel that Nolan is a very sciency filmmaker, if that makes it. Him and James Cameron as well, who strangely I
Oh,
find his films don't always equate to the man I hear talking about the science behind the stuff. But
yeah, so
uh,
I'm actually reading. I got from a secondhand bookstore the making of James Cameron and Titanic.
oh yeah,
I often George Lucas and Spielberg are very
yeah,
big for my. I
yeah.
actually like. I want to create my own Star Wars,
Ah, yes,
and that is hopefully Xanadu. But you find similarities, as I was mentioning before. James Cameron, when he's making the Titanic, it's very technical, very
yeah,
sciencey,
yeah.
and then he tries to kind of make a science project come alive in terms of a movie. So I read everything and anything I can about directors because I see them as kind of being entrepreneurs as
Absolutely.
well.
Yeah, absolutely. I mean, and it's one of the reasons I fell in love with. I got stuck in the acting stuff, but I love all the technology that surrounds these things. So yeah, it's a huge influence. Okay, just gonna double check, make sure there's no more questions, so I can hog you for a little bit longer if I don't. There we go. Okay, so we're clear for questions. So I'm going to ask you one more. Getting into this, if someone is excited about this, they go, "Wow, this is something I want to explore." What is the best route into something like this now?
Well, now that our company is like 8 years or more into things, it's very different to when we started. When we started, honestly, the first 80 or so hires all had PhDs.
Hmm.
That's quite remarkable, and that was the only way to get in.
Right.
Now, what's interesting is, we've got HR, we've got finance.
Yeah.
People need to get paid,
Yeah. Yep.
and we have a business team. We have software developers. So we have a lot of things that look like a normal company
Hmm.
rather than the early days. So the reason I bring that up is that there's room now for just non-PhDs in physics to be part of this. So that's
Hmm.
the first thing. It's like if you're in HR, check us or others out. If you're in business, check others or us or others out. So it's far more wide open now. And then I would just say, depending on whether you're in HR, whether you're want to be part of Penny Lane, so you're a
Hmm.
software developer, Python, just look at the videos that are on things. So, if you're in business in that, watch some of our videos where we've spoken at conferences,
Yeah.
or look at other companies, whatever it is, just whatever you're excited in. If you're interested in software development and maybe being part of the Penny Lane team,
Yeah.
go to
Definitely.
yeah, go to pennylane.ai and see the tutorials that we have there.
Hmm.
So another one is we hire chip designers that may or may not have come from quantum. These days, not from quantum. They're just sort of chip designers from NVIDIA,
Right.
Intel, and so forth. Then check out some of our technical papers on that and see if you get excited by the substrates that we use or the types of things that we're putting on the chip. So find out what you love, what you're interested in, and find that particular category at our company or others.
So there's a lot of different ways into it at this point now. It's
There is now, yeah,
right.
which is good.
That's fantastic. Look, I don't want to take up any more time than you have. But if you do have time for a couple more questions, I will launch in. Okay, so I guess the next question is, where do you see things? Where do you see things? I know you don't like predicting the future, but where would you like to see things in the next, maybe 5-10 years?
Well, 10 years, well, 10 years, roughly speaking, I hope many more applications have been developed that we just don't know about today. And that would
Right.
be really great. In terms of the next 3 to 5 years, for us is building a quantum data center here in Toronto.
Right.
So that's the vision. And think of that as being equivalent or having 1,000,000 qubits. So really, you've got this center or this data center that can now solve important customer problems.
Right.
So it's really those two things. Very simple to say, very hard to do, but they're our North Stars, particularly the quantum data center, because you need everyone working together in building this data center. So that's how we kind of see it.
And is that something that's going to be accessible to, I mean, maybe not everyone, but is there, what is the sort of the cost of entry of something like that? Is that going to be something that's going to be accessible like Amazon Web Services, or is this going to be a more sort of academic and big corporation type stuff?
It'll probably be everything, but heavily weighted towards large corporations. And then secondly to academic groups, because, by that time we would have raised a lot of money. We need to pay back that money and pay
Right.
it back with interest.
Right. How much money are we looking at now? How much have you raised?
So far we've raised $250 million USD,
Wow.
not including about $40 million non-diluted from the Canadian and US governments.
Wow. So this stuff is expensive.
Very expensive. When you're creating something that could be on par in terms of impact with digital computing in general and also the internet, it's going to cost a lot of money, but the return hopefully be a lot of money as well.
There's an interesting question here about whether when you're using it, can AI help you solve the problems with AI? Like, can it be used to help figure out some of these sort of interference problems or scaling up problems?
Mostly with mostly I would say with things like chip design, optimization of the architecture, things of that nature is really where it can play a role. And we'll see whether quantum and AI can merge together to give you something pretty amazing as well.
Thank you so much for this. This has just been absolutely amazing. I cannot thank you enough. This is you've taken an hour out of your time to answer some of these questions, and I really appreciate it. If people want to get in touch, maybe not get in touch, but what's the best way for people to sort of reach out? Obviously, Xanadu.AI would be the starting point, I guess.
Well, I always check my emails too. So it's Christian@Xanadu.AI.
Okay. Wow.
Either there or on LinkedIn too.
How on earth do you manage that? Because my inbox is a disaster. You've got to have some computing working on it.
I I'm very hardcore with it. I make sure I reply.
Oh, really? Oh, are you an empty inbox person? Are you like one of those clear?
Not. So I have actually I see my work inbox now. I have 70,000 unread.
Oh, okay, good.
But
So
what
you're
I
like me
do
on that now.
is, yeah, I have a star section at the top.
Right.
So anything that's important, I star, and I make sure I read all of them. Anything else, I don't bother opening. So now I haven't opened 70,000 emails. So that's like, let's say a second per email. That's 70,000 seconds.
Yeah.
Saved. So my personal one, I think, has 250,000 unopened. So I kind of structure it that way.
I feel like we're trying to sip out of a fire hose the amount of information we've got going with this. So this technology needs to help sort of reduce a lot of it for us. Are you using AI for that kind of thing as well? Your AI assistants at all? Or?
No, I haven't really got into that yet. I don't really use ChatGPT. I've tried it once or twice, but yeah, it hasn't really inserted itself in my day-to-day life yet. We'll see.
I was using it with Python, actually specifically with working with the Penny Lane stuff. I ran into some configuration issues on my side and was working with it to figure them out, which was, it's really, I've got to say, from a coding perspective, it's like having a coding, Jesus, I knocked my microphone over. It's like having a coding tutor with you the whole time. I'm very, Very impressed. Yeah.
Yeah, it's amazing.
All right, I should let you go. Thank you so much for this. Thank you to the whole team out there as well. For making this happen. Raf for taking us around as well. And I really hope that Canada continues to support this because I think it's really important that we present ourselves as the quantum power we could be. And it's fantastic.
100%, 100%.
Thank you very much.
Thank you so much.
All right, cheers. I will switch to this. Thank you so much for this. I just didn't want to waffle on in that I feel like we touched all the questions there were anyways.
No, it worked out well. Appreciate it.
And what I'll do is I'll probably pop on now after, and I've put it sort of on hold. I'll chat with people after that. But yeah, thank you so much for doing this.